Hi everybody, now that we have collected some nice knowledge about uniform integrability, we're going to look at uniformly integrable martingales and use them to prove some strong theorems. Uniformly integrable martingales are just martingales as usual, except that as a sequence of random variables, they are also uniformly integrable. Okay, so by uniformly integrable martingales, we just mean a martingale sequence that is, as a sequence of random variables, is also uniformly integrable. I'm going to use just first power uniform integrability. So we defined it in general for piece power, but we're just going to look at first power uniformly integrable martingales. Okay, here is the theorem I want to show to you in this video. So let M be a uniformly integrable. So uniformly integrable, I'm just going to abbreviate as UI. Uniformly integrable martingale. So again, it's a martingale that is also uniformly integrable. Then it has a limit. Limit as n goes to infinity of mn exists almost surely and in L1. So it's two kind of limits. It's almost sure limits and also L1 limit. Okay, and moreover, there is a very interesting and very nice property. If you want to find out what mn is, you can actually find this out just by taking a conditional expectation of this limit given fn. Everything I say here is almost sure, of course. So just look at the limiting limiting random variable, take a conditional expectation with respect to the nth term of the filtration. Of course, this is the filtration to which m is adapted to, and that will give you back the nth term of your martingale sequence, so mn. Okay, it's a really nice property. Okay, let's prove this. So let's start off from uniform integrability. By uniform integrability, so what is uniform integrability? Uniform integrability is that the supremum of expectation of mod m under the event that m is larger than c, everything in the mod, goes to 0. Okay, so by uniform integrability, if this goes to 0 in c, so as c goes to infinity, this goes to 0, I can actually pick a c which will make this smaller than 1. That's all I need for now. I can pick a c which will make this smaller than 1, since this stuff here, this whole supremum, goes to 0 with c. I just want it to be smaller than 1. And then, if I look at the expectation of mn mod, I can write this as the expectation of mn mod under the event that mn is larger than c and under the event that it's smaller than c. That's a trick we have seen a couple of times before. All I'm doing here is just adding in an indicator and its complement. An indicator and the indicator of the complement always sum up to 1, so that's all I do here. The indicator and the indicator of the complement, they do sum up to 1, so they don't do anything when I multiply them with mn mod. And then this bit here, according to my choice of c, is less than 1 from the previous line, and this is for every n uniformly. And then this thing here, well, this is easy, because under this indicator I know that mn mod is smaller than c. So this mn mod is then smaller than c times the indicator under the expectation. If I forget about the indicator, then I get a bound of being smaller than c. And so this whole business is smaller than 1 plus c for every n. It's a uniform bound on E of mn for every n. And this bound is independent of n. So it's a uniform bound. So that means, therefore, mn is bounded in L1. If I take a supremum on E of Mn mod, it's smaller than 1 plus C, so it's bounded in L1. If it's bounded in L1, then it converges almost surely. That was the upcrossing lemma and the Doomb's forward convergence theorem. So if Mn is bounded, then we have a limit. So M infinity being the limit as M of Mn exists almost surely by Doomb's forward convergence theorem. Okay, now we did prove this almost sure part. Okay, so this thing here is down here, so that's done. But then we need to show the L1 convergence. Okay, well, that's gonna be easy, because almost sure implies, it follows from almost sure that Mn goes to M in probability. Recall that when we looked at modes of convergence, almost sure actually implies improbability convergence. Then add in uniform integrability, and these together, according to the theorem we proved in a recent video, if we have improbability convergence and we have uniform integrability, then we have LP convergence. 1 and 2 were equivalent under the assumption of improbability convergence, so that implies L1 convergence. L1 because we have uniform integrability in first power. Convergence also holds. So now we have done L1. And then there is one more piece of argument which we need to show that when you take a conditional expectation of this limit, you get back Mn. So I need to show this last part here. Let's see how that works. Okay, this is gonna be a nice argument. Okay, so I'm going to fix. Let's do it in a different color so that you can see this whole thing better. Let's use this color here. Okay, so I'm going to show that stuff there. This one here. Okay, so I'm going to fix N. I'm going to fix N. And I'm going to look at R, which are numbers, integers, which are larger than N. And I'm also going to fix an event in the sigma algebra Fn. So fix all those. Okay. And then let's start looking at the following difference. I'm going to look at Mn under F and M infinity, and I need an expectation here. So expectation of Mn under F minus expectation of M infinity under F. Okay? Sorry for this notational little thing. Okay, so expectation of Mn under F minus expectation of M infinity under F. Alright. Now here is a simple exercise. If you have a martingale that is Fn measurable, that is Fn adapted, and you have an event F that is Fn measurable, you can actually increase this index N to something, for example R, and this kind of conditional expectations will not change. That's something you can easily prove using the Tower rule. So the Tower rule tells you that this thing here is equal to the expectation of MR under F. Homework, do this. So if F is Fn measurable, which we assumed here, then you can increase this index N to anything higher than N, for example R, and the expectation on this event F will not change. So that comes directly from Tower rule and Martingale property. Okay? And therefore, I now have expectation of MR on F minus expectation of M infinity on F in the mod. So in the next step, I'm going to use a Jensen inequality on conditional expectations to bring the mod inside the expectation. The mod is a convex function, so I can bring in the mod, and that just makes everything larger. So I'm going to put in the expectation of mr, so I could replace n by r first, so I'm going to write mr, m infinity, and I can actually factor out the indicator f to the end. Okay, so that was just a Jensen's inequality on mn times f, or actually mr times f, m infinity times f, and I just brought the mod inside the difference. Okay, now if I forget about the indicator, since the mod is non-negative, if I forget about the indicator, which is either 0 or 1, then I can just increase values. So I'm going to do mr minus m infinity here under the mod without the indicator. That's an upper bound. And now if I take r to infinity, then this thing goes to 0 because I have L1 convergence. Okay, so I have L1 convergence of mn to m. Here is L1 convergence. That exactly means that mr as r goes to infinity minus m infinity under the mod expectation goes to 0. So what do I conclude from here? That concludes, therefore, what I found is that this mod of the differences is 0. So whenever I have an fn measurable f, then expectation of mn on this event f is the same as expectation of m infinity on the same event f. That's what I found from this argument. Okay, and mn is fn measurable. Now if you look carefully back to Kolmogorov's theorem on conditional expectations, that exactly was the definition of conditional expectation. Mn is a version of the conditional expectation of m infinity given fn, because these two expectations under the events f are the same for every fn measurable f, and mn is fn measurable. These were exactly the defining conditions of the conditional expectation, so it follows now that mn is a version of the conditional expectation m infinity given fn, just by the definition, the Kolmogorov definition of conditional expectations. And that's exactly what I wanted to show you, because that's exactly what we're proving here.